Thank you, Emil. I want to thank the organizers first for the invitation to speak here. It's really a great pleasure. I won't be covering 15 years of work. It's not enough time, but I will tell you some selected stories how one can use single molecule fluorescence techniques to study catalysis on nanoscale particles. Now, our research in this area was motivated by the importance of nanoparticles as catalysts. They can be made from many different materials. They also have a wide range of applications. So one is always interested in studying the structure and activity correlations of such nanoparticle catalysts. Now, on the structure side, one can study individual particles down to atomic resolution in 3D, and shown here just a few selected examples from literature where you can see the structure of a single particle where every atom can be positioned in XYZ space. Now, on the activity side, they have been mainly measured at the ensemble level. So what you get is the averaged catalytic behavior of collection of particles that could be hundreds of thousands. Now, there's an intrinsic challenge in this ensemble activity studies of nanoparticle catalysts that comes from their intrinsic heterogeneity. First of all, if you look at a population of nanoparticles, there's always a morphology dispersion. Different particles have different sizes, different shapes. So a natural question one can have is that, do these particles actually have the same activity? Now, the answer is expectedly no. But more important is, how different are they? Can we correlate the distribution of structure with their distribution of activity? Now, second, even on a single particle surface, there are variable surface sites. For example, in this bimetallic palladium gold nanoparticle, there are monometallic sites. There's also bimetallic sites. So can we directly visualize which side is more active so we can understand where the activity comes from? Three is that nanoparticle structures are not static. They are dynamic, especially during catalysis, and especially nanoparticles are very small. Now, shown here is a literature example again. You can see a copper particle undergo large morphology change during the course of a catalysis, visualized by modern electron microscopy techniques. Now, besides these large morphology changes, there are also much smaller scale surface restructuring on the nanoparticle surface that are even harder to see by the latest electron microscopy techniques. Now, these structural dynamics are asynchronous from one particle to another. They will inevitably give you time-dependent activity that also differ from one particle to another. So the question is, how should one think about the temporal behaviors of catalytic activity of individual particles? Okay, so to answer these questions, one really needs to study catalysis of individual nanoparticles in real time, preferably spatially resolved. So that's what we set out to do a number of years ago now. We took the strategy coming from single molecule fluorescence microscopy. So here is our generic experimental design. We can disperse nanoparticles on a glass slide, really diluted. Then we design a reaction that is catalyzed by this nanoparticle catalyst that converts non-fluorescent reactant molecules to fluorescent product molecules. If you shine laser on it, in this particular scheme, is through total internal reflection that induces the fluorescent signal of the reaction product. One can detect the fluorescence of individual product molecules in real time. So by catching every single reaction product, one should be able to observe every single catalytic reaction by a single particle. So this reactants can be supplied in a continuous flow, so you can achieve steady-state kinetics under ambient solution conditions. Now, this so-called fluorogenic reaction approach was initially pioneered in the field of single enzyme studies by many pioneers. Now, Hopkins was actually the first one introducing this into study catalysis on micro-sized crystals of layered double hydroxides. And then we were the first of looking at catalysis on individual nanoparticles. And then Majima did it on a photocatalysis of semiconductor nanostructures. Now, when we started, the catalysis happening on the nanoparticle was sort of a thermally driven, and this was a case for the Hopkins study, and it's also for our case in studying catalysis on individual gold nanoparticles. But of course, this particle, if it's a semiconductor, you can actually couple in additional light to excite the charge carriers to drive photocatalysis. That's what Majima did in 2008. But now the underlying substrate does not have to be a glass slide. You can put onto a transparent electrode. So you can drive the reaction using electrochemical potential. So that's what we implemented in 2009. Now, of course, when you have a semiconductor and applied electrochemical potential, and you can couple the light, you can do photoelectrocatalysis, and that's what we implemented in 2016. Now, I want to show you a typical data that was taken a long time ago by a former postdoc. So this is done looking at catalysis on single 6 nanometer gold particles, a fluorogenic reaction. You don't see the 6 nanometer gold particles directly because they're too small. But what you can see is the fluorescent signal of the reaction product that is temporarily absorbed on the nanoparticle surface before the product dissolves and goes away. So each bright spot is one reaction product sitting on a one particle. So I will show you a movie that coming from this particular particle. Now the flickering is noise, but if you focus your eyesight to the center of the movie and you see these fluorescence flashes, okay? So each flash is one reaction product, which means one catalytic turnover catalyzed by one particle. Now this movie is actually playing in real time and it runs for more than an hour. So now one can integrate the fluorescence intensity, which is the brightness, and plot it as a function of time. And so you see these characteristic off and on signals. Each sudden intensity jump marks a catalytic product formation event. The products will stay on the nanoparticle for a certain amount of time and then will suddenly dissolve. As soon as the product dissolves from the nanoparticle surface, it'll undergo rapid diffusion in the solution. It'll be carried away by a solution flow, so we won't see it anymore. So each off and on cycle is a single catalytic turnover by a single particle. So now one can further zoom in into this fluorescence image. One can see the fluorescence of the reaction product sprays over a few camera pixels. Okay, one can plot this fluorescence image in three-dimensional fashion. X pixel, Y pixel, number Z is number of photons. So this fluorescence of a single molecule appears as a mountain with a width about 400 nanometer in width, much bigger than the actual physical dimension of 1 nanometer sized molecule. So this is so-called diffraction limited width, well known in the field. However, because of a large number of photons one can detect, one can localize the position of this individual molecule with nanometer precision. Again, this is a well-known single molecule super localization technique. Okay, so with this, one really have a real-time single reaction resolution and also nanometer precision and resolution measurements of individual particle catalysts. So one can utilize this type of data to look at the catalytic kinetics, to learn about the mechanism, to monitor dynamic events over a period of many hours. Of course, one can evaluate heterogeneity by comparing the behaviors of one particle versus another versus another. Now, all of this is built on the fact that the reaction you're studying has to be fluorogenic. Okay, so one of the product needs to be fluorescent. So over the years, we have discovered a number of fluorogenic reactions. They are catalyzed by different catalysts. They also represent different chemical transformations. Now one can look up two of the reactions. For example, this molecule can undergo half reactions on an electrode. And so you can probe electrons or probe holes using this type of approach. Now you can even look at the literature, and there are actually many fluorogenic reactions available. Listed here, just a few selected examples, okay? They're all fluorogenic. They also represent complete different chemical transformations. So if you are interested in a particular chemical transformation, a corresponding fluorogenic version might be already there, okay? Or you talk to one of your creative synthetic chemists, maybe they can design molecules to make your desired reaction fluorogenic, okay? Now, we have applied this approach to many different sub-areas in heterogeneous catalysis. We started looking at individual particles of thermally driven catalysis. We moved on to electrocatalysis, photoelectrochemical, photocatalysis, plasmonic catalysis. And now, today, I will tell you a technique that will enable us to looking at reactions that are not fluorogenic, okay? They do not require fluorescent signals. So that's a technique called COMPEITS. And I will tell you how we can study molecular adsorption on surfaces of nanometer particles. The last topic of polymerization catalysis is using a complete different technique called magnetic tweezers, which I will not cover. At the end of today's talk, I will also tell you a short story how one can study photoelectrocatalysis on semiconductor particles. Okay, so far I give you sort of a brief history, at least mainly what my group have done using fluorogenic reactions, and then resolving and detecting reactions on individual particle. Now, most of the reactions people study or people are interested in do not involve any fluorescent species. So what can we do? Can you at least achieve similar type of imaging on non-fluorescent processes? So I'll tell you a technique called COMPEITS that was implemented by my former postdoc, Shen. That stands for competition-enabled imaging technique with super resolution. Now, I have told you at this moment, if you have a fluorogenic reaction that can be catalyzed on a catalyst particle surface, by detecting and imaging and localizing individual product on the catalyst surface, one can image this reaction at nanometer resolution, okay? Now, if you have another reaction that neither the reactant nor the product is fluorescent, however, if this reaction happens on the same catalyst particle surface where the reactant will compete with this fluorogenic reaction on surface sites. Once you introduce this competing reaction, then the original fluorogenic reaction rate will be suppressed at all the possible surface sites. And that suppression can be mapped at the same nanometer resolution. And that suppression essentially tells you the magnitude of suppression essentially informs of something about this competing reaction that does not carry a fluorescent signal, okay? So we decided to implement this to look at photoelectrocatalysis or photocatalysis on bismuth vanadium particles. They have well-defined morphology, and one can assign a surface facets just based on the shape of the particle. Now, the target reaction we decide to first look is the oxidation of hydroquinone to quinone. Hydroquinone and quinone are not fluorescent in the visible range, okay? They are fluorescent in the very UV range, but not in the visible range. And then the fluorogenic reaction, which is essentially a probe reaction now, it could be any, and we just decided to use this particular one by detecting the fluorescent signal of this particular reaction product. Now we first, of course, have to confirm these two reactions indeed compete. So here you can do conventional bulk kinetic studies by monitoring the fluorogenic probe reaction rate as a function of the competing hydroquinone concentration. You can see with increasing concentration of competitor, the fluorogenic reaction rate decreases. You can also measure this particular reaction rate by monitoring the absorption appearance of this product, and again in bulk assays, and you can see it increases in an anti-correlative fashion. So these two reactions indeed compete with each other on the surface of the catalyst particle. So now we're ready to do this COMPEITS imaging. So first, we can map out the fluorogenic reaction on a single bismuth vanadium particle whose SEM image is shown here. And in the absence of our competitor, okay, you can count the number of reaction products at every single location over a period of time. Then you can introduce your competitor hydroquinone at a particular concentration. You can see the reaction rate suppresses at all the possible locations. Now then you can take a difference of these two images. Actually, in the inverse space, it turned out if you take a difference in the inverse space, this particular number is linearly proportional to the equilibrium absorption constant of the hydroquinone on the surface. Okay, so this image, we call it a COMPEITS image. Okay, so now if you look at the image, you can immediately tell that the hydroquinone absorbs on the basal plane stronger than the lateral facet, and then followed by the corners. Okay, now you can even dissect out a single facet and do a more careful titration by measuring the fluorogenic reaction rate as a function of the competitor concentration, and you titrate carefully, you actually can fit this curve, you can obtain the absorption equilibrium constant of the hydroquinone on a specific facet, on a single particle. Of course, the equilibrium constant will give you a Gibbs free energy directly, okay? Now, what we have here now is a quantitative way of mapping non-fluorescent reactions, and here the reactant absorption at super optical resolution, about tens of nanometers spatial resolution. Now, since we are talking about absorption now, so let's step back and look at why absorption is important to look at in the first place. Well, absorption is important in heterogeneous catalysis that allow you to activate the reactants, eventually go to the products in a surface catalyzed reaction. Absorption is important for separation, for sensing. Now, if you're into making shape-controlled colloidal particles, the absorption of ligands on the surface gives you the control of the colloidal nanocrystal shape. Okay, so it's important to quantify the absorption of all kinds of adsorbates on surfaces, but they are hard actually in general. You have to differentiate adsorbed versus free species. The amount of adsorbates on surface is always miniature. If you do it in solution, you have to worry about solvent interference. But now if you have a surface that is inhomogeneous across different length scales, especially at nanoscale, it will make it even harder to do, okay? So what you here always want is a higher resolution and quantitative imaging approach. Of course, there are many powerful surface science techniques already available. Of course, my favorite right now is using COMPEITS to image. One can resolve absorption at nanometer resolution on individual particle. So my current postdoc, Rocky, decided to implement COMPEITS to study absorption of ligands on gold nanoparticles, including pseudospherical gold particles about 5 nanometer in diameter, or gold nanoplates with well-defined facets, or gold nanorods that have a different morphology, again, with well-defined facets. A set of ligands he decided to look at include CTAB, or analogs, PVP, which is a polymer, halides, and also thiol. So these ligands are either shape-directing reagents that allow you to control the shape of colloidal nanocrystals, or they are stabilizers of nanoparticles, or they act as inhibitors in surface catalysis. Okay, but turn out most of them actually lack quantitative absorption information in the literature. Okay, people use them extensively, but very little is known about, let's say, the absorption, even affinity on any particular surface. Okay, so Rocky decided to look at these things, and of course he chose the fluorogenic reaction as a probe, and this is shown here. Now, if you think about surface absorption, perhaps the most widely used model to understand surface absorption is Langmuir absorption. Okay, in Langmuir absorption, which is a non-cooperative absorption, one can measure the surface fractional occupation as a function of ligand concentration in the surrounding, and it follows a saturation curve. Initially increases, eventually flattens out. Now, if the adsorbate on the surface adsorb cooperatively, you can have this sigmoidal isotherm and give you a positive absorption cooperativity. Now, this behavior can be described by the classic model called Hill model, where the h on the exponent is a Hill coefficient. So for positive cooperativity of molecular resorption, h is bigger than 1, which is actually sort of a number that tell you the number of co-adsorbed molecules simultaneously every time. Now, you could also have negative cooperativity in molecular resorption, where h is smaller than 1, but bigger than 0. Now, you can rearrange this equation into a linear format, okay? And now in this linear format, the slope here is a Hill coefficient, which again is a numeric number that quantify cooperativity. Now, with that in mind, Rocky looked at it. For example, first, C-type adsorption on single 5 nanometer gold particles. You measure the fluorogenic reaction rate on this a single 5 nanometer gold particle, titrated against C-type concentration. Of course, the rate is suppressed with increasing the competitor ligand. Now, if you fit this data using this equation, where this is a competing term, if you set h equals 1, which is the Langmuir adsorption, the blue curve actually doesn't fit the data. In order to fit the data satisfactorily, which is the black, the h has to be about 2, which give you a Hill coefficient of 2, which is bigger than 1, which means positive cooperativity. Obviously, we can immediately extract out the adsorption equilibrium constant of C-type here. Okay. Now, again, you can rearrange the data into a linear format. The slope here is 2 and bigger than 1, give you positive cooperativity. So we think it's due to when C-type adsorbs on the gold particle surface, the long acyl chains give you attractive interactions and they give you positive cooperativity. Okay. Now you can study this similarly, looking at the polymer PVP, and you titrate it. It turned out Hill coefficient is 0.6, smaller than 1. So PVP adsorption on gold nanoparticles have negative cooperativity. Okay, so we think it's because at neutral pH, this polymer is positively charged, so you have electrostatic repulsion and give you negative cooperativity in adsorption. Now we also look at halides, for example, iodide or bromide or thiol. They don't show any cooperativity at all. They can be fully described by the classic Langmuir adsorption model. Okay, so all of this will tell you that we can discover positive and negative cooperativity on individual particles, and it varies depending on the type of the adsorbate they're looking at. Now, we don't just measure, of course, one particle. In a wide field imaging, we can measure hundreds of particles in parallel. Okay, so for example, for C-type adsorption, we measure many individual gold particles. You can extract out the Hill coefficient, and you can extract out the adsorption affinity for every single particle. You can see you have a clear negative correlation. With increasing affinity, the H value is approaching 1. Okay, 1 is no cooperativity at all. Okay, so stronger adsorption, weaker cooperativity approaching 1. Now, you can also look at the negative cooperativity case for PVP. Again, with stronger adsorption affinity, H is again approaching 1, which is no cooperativity at all. So this anti-correlation tells us when you have stronger adsorbate surface interactions, you have weaker adsorbate interactions. And that's the anti-correlation by analyzing the statistical properties of a collection of individual particles. Now, 5 nanometer particles is too small for our spatial resolution to resolve within a single particle. But we can choose to study particles much larger, for example, gold nanoplates, which is large enough now that we can resolve adsorption on this top 111 facet or along the edge, which is dominated by 110 facet, or around the corners, which is also dominated by 110 facet. Okay, so you can generate the COMPEITS image. This image is a little noisier, but this image is proportional to the adsorption equilibrium constant. Again, we can clearly do a careful titration to extract out the adsorption equilibrium constant at corner edge and facet regions. So you can immediately tell that the adsorption is stronger on 110 facet than 111 facet on a single particle. We can extract out the corresponding Hill coefficient that give you the cooperativity. Again, they are all bigger than 1, so you have a positive cooperativity, but you have an anti-correlation between H and then the K. Again, it tells you when you have a stronger affinity, you have weaker cooperativity even within a single nanoparticle. Okay. Now, we can obtain similar results of looking at PVP, which is a polymer ligand in this case. Now, at the end of the day, what we obtain here are quantitative knowledges about molecular adsorption on individual particles at different facets. Okay. So we wondered is that with this quantitative knowledge, what can we do something with it to utilize it for some functional applications? Now let's take a step back, looking at, again, molecular adsorption behaviors, how we understand it in theory. Okay. So typically, again, the density of adsorbed ligands is the maximum possible density multiplied by fractional occupation of theta. Now, this fractional occupation is quantitatively describable by the adsorption equilibrium constant and also the Hill coefficient to the top. Okay. Now, this density of adsorbed ligands is a quantitative metric. Is a quantitative metric of the surface stabilization by the ligand adsorption. It is also a quantitative metric of accessibility of the surface to other reagents. Okay. Now, if you plot out this rho as a function of the ligand concentration, of course, this equation is an apparent saturation curve, and it eventually will saturate to the maximum ligand density on the surface. So if you have any surface, it should look like this qualitatively. Now, if you have two surfaces that differ in their adsorption affinity, the stronger adsorbing surface would have a curve look like that, where the green curve is on top of the magenta curve. Okay, that is what is presumed most of the often. But turn out this presumption, where the green curve on the stronger surface is above the magenta curve of the weaker surface, is only true under a condition where the maximum density on the green, stronger adsorbing surface is larger than the magenta, weaker adsorbing surface. Okay, so this condition has to be satisfied for the two curves behave like this. Now, if the maximum density on the green, stronger surface is actually smaller than the maximum density on the magenta, weaker surface, these two curves actually cross, okay, at a particular critical concentration. So what it means here is now on the lower ligand concentration condition, the green surface will be more covered, more stabilized, but on the right side, the magenta surface will be more stabilized, more covered, okay? Now we wondered, we call it a so-called crossover effect. Does it really actually exist? And also suggests by simply changing the ligand concentration, we can change the relative stabilization of different facets. Okay, maybe we can utilize this to do a control of colloidal particle facets. So my postdoc, Ming, decided to implement this to look at the synthesis of colloidal gold particles in the presence of CTAP. So we know that CTAP adsorbs on gold 110 facet stronger than 111 facet. Now, if the 110 facet has smaller maximum density than the 111 facet, the two curves should look like this, where at low concentration, 110 should be a dominant facet. At a high concentration of CTAP, 111 facet should be a dominant facet. Okay. So he made the gold particles by keeping every condition the same. The only thing changes is the CTAP concentration. Okay. And you see, you start with irregular shapes and eventually get sort of pristine gold nanoplates. You can do so-called lead under potential deposition in this cyclic voltammetry, you can actually resolve the 111 facet and 110 facet. So at this particular low concentration CTAP, 110 facet is dominant one. But at a high concentration, the 111 facet is a dominant one. And with increasing concentration, you have a progression, okay? And you can analyze this data, you'll see that the fraction of surface of 111 facet increases, 110 facet decreases, and they have a crossover, okay? So what I've demonstrated here is that by changing the ligand concentration, you can change the facet control. I should say that using ligands to manipulate nanoparticle shapes and nanoparticle surface facets is a well-known strategy in colloidal particle synthesis. But what's new here is that you only need to change a single ligand. Only the single ligand concentration, you can already manipulate the facet dominance. In the last few minutes, hopefully I can quickly tell you something about photoelectrochemical catalysis. To set everybody on the same page, so here is a genetic diagram of photoelectrochemical cell. On the photoanode side is a semiconductor. You have a valence band, you have a conduction band. You excite, and you can generate holes and electrons. At the semiconductor electrolyte interface, you have band bending. The holes migrate to the surface, and you can oxidize water eventually to oxygen. Electrons are extracted away because of same band bending towards the external circuit, and you can generate a current, and the current can be delivered to a cathode to reduce proton to hydrogen. Okay, so in this process, the band bending at the semiconductor electrolyte interface is important for charge separation. Of course, all these key processes depends on the material that you study. Okay, a real semiconductor material does not look like a cartoon box that I drew here, but maybe looking like this with many particles that are stacked into a thin film. Or one can also look at semiconductor particles with well-defined shapes that you have different surface facets, such as bismuth vanadate. The turnout on bismuth vanadate, it has a right band gap for absorbing visible solar light, and also the valence band has sufficient energy to oxidize water to oxygen. And it is also known that bismuth vanadate, these two facets have different work functions, or which means they have different energies, where the 110 facet is slightly higher in energy than 010 facet. So if you're excited by light, the electrons tend to accumulate on this basal facet, where holes tends to accumulate on this 111 lateral facet. Okay, so you have a natural charge separation between different facets. This has been demonstrated by Kelly using bulk SEM imaging. Now in this diagram, there's a gap between this side and that side that I did not draw. Of course, in reality, these two facets do not have a gap. They actually meet at an inter-facet edge. So which means the energy levels on both two facets have to connect through a transition zone, okay? Now, this transition zone essentially is band bending on the nanoparticle, on the semiconductor particle surface, okay? And the question here is, how wide is this transition zone? Now, you may wonder why the width of this transition zone would matter, okay? Why would it be important? Now, let me tell you. Now, if you have a two-dimensional material, two different semiconductors that meet at a line, it's known that this transition zone of energy band bending is about hundreds to thousands nanometers in width. Now, if you have a three-dimensional junction, it turned out the width is only about a few nanometers in size. Now, what we have here is looking at inter-facet junction that between two surfaces, which is similar to this case, different from this case, but is not exactly the same as this, because yes, you have two surface states, but the surface states are not confined to exact the same surface. They maybe include different sublayers. And also they are on the same three-dimensional particle where the interior is shared and is identical, okay? And so I draw this band bending diagram now in this three-dimensional space where the X is a direction that goes from one facet to another. But let's say if this case, inter-facet junction is similar enough to this two-dimensional junction, then you will have a width of hundreds to thousands of nanometers that become actually comparable to the particle size. Okay, your particle size is only nanometer to microns in size. So if the transition zone is at similar size, then the transition zone will dominate this particle behavior. Okay. Now, if you put this particle in contact with the electrolyte, and then you have the solid electrolyte band bending at the interface. On this facet, the band bending is less steep. On that facet, the band bending is more steep. You're going from one facet to another, the band bending gradually change, going through this transition zone. So at different locations on the same particle surface, you would have different photoelectrochemical properties. And the difference goes through the transition zone may dominate the entire particle behavior. So my postdoc, former postdoc Shen, decided to look at this. I mean, how wide this transition zone is, can we determine it? So he implemented a multimodal functional imaging platform. So he made a photoelectrochemical cell. He put bismuth vanadate particle on an ITO working electrode. He coupled multiple lasers into the microscope. And then first, he can use a 4-5 nanometer laser to excite charge carriers, but focus down to a diffraction limited spot. So you can measure local photoelectrochemical current at different locations and scan from one facet to another. So that's what he did. The circles are the laser focus spot and the positions that are scanned along one dimension on this particular particle visualized by SEM. And you can see that the photocurrent coming from water oxidation goes through a S-like transition zone. And this transition zone is about microns scale. But this measurement is only diffraction limited by the laser spot size. Okay. We want to improve our spatial resolution. So Shen implemented the super resolution reaction imaging. Now he used fluorogenic reactions that probes surface holes and surface electrons specifically by generating a fluorescent reaction product that we can do single molecule fluorescence imaging. The reactions are shown here, I won't get into. But now by mapping out every single reaction, now you can map out the whole induced surface reaction and electron-induced surface reaction. You can actually differentiate between two different facets. You can quantify the whole reaction rate as a function of position, and electron reaction rate as a function of position at many different electrochemical potentials. Again, you can see the S-like transition zone. Okay. Now we can do a careful electrochemical potential titration plus quantitative modeling. We can extract out the flat band potential. We can also extract out the charge separation efficiency. Okay, so you see the flat potential looks like a S-like transition zone of microns in width. And here is again, the anti-correlated transition zone with microns in width. And then we can quantify, let me jump through this. We can quantify the width here is about 2 to 3 microns. Okay. Now, so this is a picture that emerged from the quantitative measurements. You go from one facet to another. The two facets have different energy, but they meet at an inter-facet junction. And this junction behaves like a two-dimensional junction that give you a wide transition zone. Because of the transition zone, the band bending at the solid electrolyte interface is different from one facet to another and slowly changes along the surface. Okay. And we also determined that transition zone width is independent of the particle size. Now this behavior, again, would predict it would affect the behavior of the entire particle. Okay. So now can we look at this? What about the effect on the whole particle? So Shen implemented the third strategy that now you shine a laser on it rather than focused, you defocus a little bit so that the laser spot cover the entire particle, just measured a single particle property. Now he measured the photocurrent density as a function of a particle surface facet size in this particular facet or the other particular facet. The dots are the individual particles he measured, and the surfaces are the general trends. Now, one can think about this before I take you through the data. One can think about what would you expect. This Bismuth vanity particle has two surfaces. We know the lateral facet, the green, is more active, where the orange facet is less active, and then it goes through a transition zone, very wide in width. Now, if you keep the left side, the green facet constant, and then increasing the facet of this orange side, so you go this shape into that shape. So you'd expect the specific activity would decrease and eventually flatten out, okay, because decrease eventually flatten out. That's indeed what we saw. So you have a decrease, and then eventually flattens out, okay? Now, if you keep the right side the same in size, by making the left side, the lateral facet larger and larger, you essentially change the particle shape in this way. So you should expect the specific activity would increase and then flatten out, saturates. That's indeed the case. So we have this increase and then eventually saturating behavior. So essentially, this particular transition zone really dominates the shape-dependent behaviors and size-dependent behaviors of this particular particle in photoelectrochemical behaviors. Again, and then this behavior is dominated because of the surface transition zone width is comparable to particle size. Now, at the end of the day, we also ask ourselves, can we manipulate this surface transition zone, make it wider or narrower? The answer is yes. So we can do chemical doping, and I won't be telling you this. Its details is in this published result. Now, I want to finish here, and hopefully I'll give you a brief history of single molecule fluorescence detection in looking at nanoparticle catalysis. I introduced a technique called COMPEITS that allow you to look at nonfluorescent processes at super optical resolution. We applied the technique to look at ligand adsorption on gold particles. At the end of the talk, I told you something about photoelectrochemical behaviors of individual semiconductor particles, in particular, this inter-facet junction effects that are analogous to two-dimensional junctions in semiconductor photoanodes. I think the people who I mentioned who did the work. These are the funding agencies. Again, thank you for the invitation. Thank you for your attention. I'll be happy to answer any questions.
Okay, thanks a lot, Peng. Really nice. A lot of work.
Sorry, I was a little slow.
Yeah, no, it's fine. So questions for Peng? Yeah, okay.
Really nice work, and it's very nice that you can see this non-fluorescent reactions from this competitiveness to the fluorescent one.
Yes.
But I'm worried that in case that the second component, the non-fluorescent, would only absorb and not do catalytic activity, you would see the same effect. So how can you distinguish between the passive absorption and an absorption plus catalytic activity?
Yes. So the technique right now does not tell us the subsequent turnover to make the product. To ensure the subsequent product is formed, you essentially have to do this conventional ensemble measurements and to make sure the reaction indeed formed. That actually showed, of course. What you also point out is that pure surface absorption will give you the similar suppression and competition. That's exactly what we utilize for in the ligand absorption study. Yes. So for the measurements to work, you don't need a reaction. All you need is absorption.
Exactly.
Yeah. It's very true. Yes.
Yes. So I have slightly follow-up questions. So exactly. So at some point you assume the reaction sites are the same for both, but it might be like an aesthetic effect, right, from the competing reaction, so that it blocks the surface. But it's kind of like on the same.
Yeah. So this is why that the information we extract out is quantitative behavior of the reactant absorption, not a catalytic turnover. So it didn't mention allosteric effects, did you? Yeah. So the allosteric effects is sort of a remote effects where that you say you absorb somewhere else and affect reaction somewhere else. And then the reaction, the probe reaction is what we measure. For that case, we won't be able to tell. Okay. And but how can we rule out that? Well, of course, once you measure this data and then you fit your data with a quantitative model, and of course, what we can get is the simplest model that give you this behavior. Now, if you add in allosteric effects, is a more complicated model.
Yeah.
Yeah. Unless the data require that, then we don't get information like that.
Yeah. So
Yes.
it's a beautiful talk, and I think it's really opening for, especially for chemists, many eyes and many new directions are opened. From the single molecule physicist, I'm sometimes thinking that there's always a convolution of how you achieve your signal with what is happening. As an example, if you see fluorescence on a nanoparticle, you also think that the nanoparticle will quench the fluorescence, and then there are sites which will quench more and less and might have plasmonic enhancement or whatever. So how do you account for such effects? I mean, a nanoparticle will quench a dye completely if it's adsorbed, right?
Actually, not true. So it turned out the surface quenching of fluorophore on gold particles is size dependent. That's what we found out. Now, on the 5 nanometer gold particle, the dye that we detect, the fluorescence quenched about 50%. You can compare its intensity on the particle versus on a cover slip. Okay, and it's about 50%. Typically, people say quenching does not give you a quantitative means. Quenching occurs, but the 50% of the fluorescence is sufficient to detect. So what we found out is that if we want to detect this fluorophore on a particle that is hundreds of nanometers in size, we had actually extreme difficulty, okay? And we think the fluorescence is quenched significantly for detection. So we actually had to implement a technique, let's say a trick, that we encapsulate the particle with a mesoporous silica shell, where the mesopores allow the reactants to go in, react. When the product is formed, we don't directly detect it on the surface, but detect it when it's temporarily trapped in the mesoporous silica shell that is some distance away. Okay, so that's what we had to do. Now, on the semiconductor, actually, the quenching does not occur. He also asked, what about quenching or fluorescence variations will give us a measurement bias, okay? Now, it turned out, first of all, we don't measure fluorescence intensity. We count the number of molecules, okay? So as long as you can count the number of molecules, it's okay. But you say, well, the fluorescence intensity will bias your counting, okay? And well, because for every molecule we measured, not only we know the molecule is there, we also know its intensity that we measured. So we can compare the intensity measured every single molecule at different locations to make sure that we're not biased. So if you have, say, at one particular location, the fluorescence is much stronger than the other one, especially when you have a plasmonic particle, then you have to account for that. And in the case that I presented here, it doesn't occur. But in another case that we do have similar things like this, we have to correct for fluorescence differences at different locations. Yes, these are all very good points. They are all technical details that one have to pay attention to. Yeah.
So in the case, in the ligand exchange for the flat gold surface,
Yes,
you
yes.
also have like a porous layer?
Yes, we actually, yes. Actually, I didn't cover it. I went through it quickly. Yeah, so for example, in this particular case, is actually covered with a very thin shell of mesoporous silica, okay, and where we detect the product in the shell rather than on the particle surface directly.
Very nice talk, thank you. I was
Yes.
wondering, do you see any temporal changes in the COMPEITS technique when you have, let's say, a reduction of your frequency of produced fluorophores?
Yeah, not in this case. So we always have to check the stability. Essentially, let's say we can measure this probe reaction rate as a function of time, and then you can measure for a number of hours. We make sure what our measurement is time independent. Well, there are indeed cases that you have so-called inhibition, and then you can see the activity decreases. So we essentially narrow our measurement within the window that the catalyst is stable, yes.
So you don't see any differences that some sites may temporarily absorb more or produce more fluorophore?
No, well, I do, but I cut that part of data out. So I only measure the stable version, period. Okay. So for example, in the reported results, we'll say the catalyst activity is stable for 3 hours, and beyond 3 hours, and we don't look at the data. Yes.
Any other question? Yes.
Yes. Yep, you can call that way. Yeah.
That width should depend on the charge carrier density.
Yes.
In a complicated fashion, in particular, because you are illuminating this.
Yes.
Does it roughly quantitatively agree with what?
Okay, so so the charge carrier, it turned out because our measurements have to be done at light condition, because we're using this photoelectrochemical as a probe, okay? And now it is indeed on the charge densities, but not charge carrier. At least within our light excitation intensity, we don't see a difference in width, okay? But what we could do is more dramatically, this is actually shown here with the little things. We can dope the bismuth vanity particle of nitrogen doping by treating it under annealing. It turned out when you treat it under nitrogen, you change this dopant density on two different facets differently. Now this transition zone,